Well, I guess I wasn't. So we spent the last 4 classes, which is a good practically 1/3 of the course on the Greek geometry. The Greek geometry is very, very important because after the Greeks, the Arab nations made copies of the Greeks. The Greek stuff got burned, and the Arabs did advanced the Greek math. So it was kind of like it evolved. Everything evolved from the Greek math. The Chinese math kind of evolved on its own separately, and the Babylonian and Egyptian, it exists because surely it contributed to the Greek understanding. And then eventually in the Middle Ages, math comes back to Europe. So today I have some snippets from several different time periods. And the first one is from 100 AD. And it's actually still the Greeks. It's spelled this way. I always pronounce it Ptolemy. Ptolemy.
Oh, I know this one. This one's cool.
So Ptolemy was studying, and a lot of math was invented for the purpose of studying astronomy. Of course, there wasn't that much to do at night. You look up, that's the biggest mystery. What's going on? I see certain stars, I see certain planets, I see the moon, I see the sun. How can we predict, and they follow cyclical patterns, so they are predictable. If the stars are in one position, 24 hours later, they're almost the same, but they've all moved a slight bit. So Ptolemy was mainly an astronomer. He wrote a book, I think it's called the Almagest. I'm not sure if that's how you pronounce that. And in that book, in order to analyze the positions of the planets and the stars and the moon and the sun, it was necessary for Ptolemy to essentially invent trigonometry. Now, we've mentioned trigonometry because the Chinese did a problem, the Sea Islands, that had a hint of trigonometry in it. But you don't have trigonometry until you're basically using a table nowadays, with sine, cosine, and tangent. If you're using these tables that people made, you're doing trigonometry. So what Ptolemy had to do was create these tables. But the table he created was not the table of sines or the table or cosine tangent, the one that we're familiar with. But he created something that's called the table of chords. Now, what's meant by the table of chords? And I actually have over here, I'm working with only one window today, so I'm not, if you come over here, I have a nice, it says chords. What's meant by a chord in like the table of chords is, see, I take the slider. If I make it 50, this angle, there's an isosceles, this is a unit circle, and there's an isosceles triangle here with a 50-degree angle. And depending on what the angle is, these two sides are length 1, but the length of the base in this case is 0.8452. The bigger the angle, a chord is a chord is a line segment that joins two points on a circle. So the chord is from here to here. And the bigger the angle, the bigger the chord. The biggest the angle can get is 180 degrees. And at 180 degrees, this would flatten out to basically, that third side would just be the diameter, and it would be 2. And
Wow.
if the angle got down to 0, then the chord would be 0.
So is this the first unit circle?
Yes, it is like a unit circle. I mean, he didn't always make the he didn't always
He didn't call it a unit circle.
he didn't always use a radius of 1.
Oh,
I
okay.
think sometimes they use really big radius because they didn't like using the decimals. So
Right.
like they might be a radius of 21,600, you know,
Okay.
something like that. But it's like, yes, it's like a unit circle. It's a circle at least, and we're thinking about like the distances. Now, one thing that's unfortunate, like if I look at chord 30 and it's 0.5176, and I double, so that's 30-degree angle in the middle here, and I double the angle to 60, it would be nice if the chord doubles, but it didn't. So it's not that if it was as easy as, oh, if I double the chord, if I double the angle, it doubles the chord, and if I triple the angle, I triple the chord, we could easily figure out all these chords. But see, chord 60 is 1. And let's start that off as our first fact. We say chord 60 equals 1. That's because if it was a 60-degree central angle, this isosceles triangle wouldn't just be an isosceles triangle, but it would be an equilateral triangle. Now, there's only one other chord, maybe two. Another chord that's not too bad is chord of 90.
Square root of 2?
It is the square root of 2. Because if my chord is 90, this isosceles triangle is actually an isosceles right triangle. And either you know your 45, 45, 90 rules, which says that I have side square root of 2, or you do the Pythagorean theorem. X squared equals 1 squared plus 1 squared.
So the name of these chords are coming from the angle that's between the two chords?
No, those two things aren't chords. There's only one chord in the picture.
I'm sorry, between the two radii, I should say.
That's right. The angle is the inscribed angle. I'm sorry, the central angle between the two radii. You know, you don't have to know. I should mention, you know, so some people in the class have different backgrounds. So some people know side square root of 2. But even if you don't know that, you don't need it. You see, you could use Pythagorean theorem. Now, Pythagorean theorem has come up over and over in the different things. So some people might say, oh God, I don't know all these rules. Well, you know what? You don't need that rule. Yes, it might take a few seconds longer to use Pythagorean theorem, but I think, you know, we could all say that Pythagorean theorem is a thing that comes up so much that even if you had to refresh on it, you know, it's fair to ask you to.
But it would only work for chord 90, right? Because it has to be a right triangle to actually pull that off, right?
Right. That's why we only have 2 values right now.
Okay.
There's only 3 easy values.
I gotcha. Okay.
But take a look: 60, 90.
Yep.
$1.414. I think the only somewhat easy one is chord 120. I think that's not too bad. Oops. Why is 120 not like so bad? These are the only ones that we could even get without some real cleverness coming. Anyone have a thought about chord 120?
Isn't that another special triangle? Like if you take that in half, that's 60, and then it creates a 60-90 triangle, maybe?
That's right. If we split it in half, it turns into a 30-60-90 triangle.
Yeah.
In a 30-60-90 triangle, which we've seen before, we end up with the short side is half the big side, and the long side is the medium side, sorry, is square root of 3 times the short side. But that's not chord 120. That's only a piece of it. What's the entire chord 120?
Oh, radical 3, because you add them together.
Yeah.
That's right. And by the way, some people asked about like formulas. You know, I wouldn't mind giving you, like, for instance, S root 2, you know, 45, 45, 90, you know, 60, 30, S, 2S, S root 3, you know, little things like that. I might give you some things like that, little references, but no, I wouldn't give you like, for instance, let's think. I wouldn't give you, you know, in the spiral, you know, the length of this, you know, line segment is, you know, theta over, you know, whole thing. Because I might give you a couple of little things, you know, because some people are like sort of at a disadvantage because they don't have maybe these things at the tips of their fingers. So I'm gonna think about it. I asked somebody in the class to make me a list of the sort of facts, because they said I'm memorizing so much. So what do you think would be fair facts to have?
Can we send supplemental proposed formulas to you as well?
Yeah, I'd be curious. Listen, even if I say no, the
Right.
creation of that proposal might help you.
Remember.
You might also realize there's not as many as you thought once you
Right.
start listing them. And you're like, oh, wait, here's my list. It's only 8 things. Maybe it's not such a bad list, you know. So it'll be interesting to do that. You know, something I was thinking just on about like the final, for instance, remember this question? Sorry, 4, 9x altitude drawn to and I said, okay, we solve this by doing, you know, 4 over x equals x over 9, which you could either get by similar triangles or by just knowing this rule. So let's imagine I gave you on a formula sheet a, b, x, a over x equals x over b. Well, then this would no longer be a question on the test. There might be some other question that involves the formula, but it wouldn't be this. You know, maybe it's the squaring of the rectangle. You know, and I say, what's the area? I guess what I'm getting is that once you're given a formula, certain questions become certain pretty easy questions get disqualified from being questions on the final.
Oh, so what you're saying is that if we come armed with what you're calling formulas, then the questions have to kind of step up their game.
You know, I don't want to scare. Yes, it's not like in a vindictive sense or anything. But,
No, I know what you're saying, because I do it when I give tests to middle school and high school. It's like, if you know more, or if you're coming with more, then in order to test what you're thinking, I have to challenge it. I get what you're trying to say. You have to challenge. All right.
Like this question would be a perfectly good question if you were not given the formula.
Right, I understand what you're saying. It's
So
like going to the algebra regions and not having that reference sheet.
Yeah. So I'm not saying that this is necessarily a question, but if it was, and then
Mhm.
suddenly I gave you this formula, that would no longer be a question. Maybe some question that, that involves the formula.
Right.
So it's just something that's why I don't love giving too many formulas, because it does restrict me in certain fairly easy questions that I want to give.
We don't
Okay,
want to give up the easy ones for sure.
Right. It's like a strategy. So
Right.
currently we have only 3 chords. And by the way, when I come over here and I go to chord 120, we see it is square root of 3.
Yeah.
But aside from those 3, we don't know any, so currently I have a list. Chord 60 equals 1. Chord 90 is equal to the square root of 2, which is about 1.4. And chord 120 is
Square root
equal
of 3.
to about 1.7.
Mhm.
Oh, I'm showing the wrong thing. I could get a little bit sneaky. Like if I want to know what chord 30 is, which is half of 60, I could be a little bit sneaky and say, if I know chord 60 is 1, and I make, if I cut this in half, this would be 30 and 30. And then I bisect this angle and this angle. Then this line segment right here would be chord 30. However, check it out. If I take half of one of those triangles with the 15 here and the 30 there and the half here, because the whole chord 60 was 1, so half of it is a half. And this is 1. And this is radical 3/2. I could, in theory, which I'm not going to do, use the angle bisectors theorem to get chord 30 but it would be hard. One of the surprising chords that we hold on a second, let me just make sure I say this right. A surprising chord that we actually already know, believe it or not, is chord 36. You might say chord 36, no way. Why can we get chord 36? Anyone want to just sort of say, does that look familiar at all?
The golden ratio, maybe?
That's right. It's a
Yeah.
golden ratio, except this side is 1. So it ends up being like 0.6018. We usually do it with the base being 1. So it's basically 1 over the golden ratio, which is actually also equal to 0.6018.
Mm.
Take a look over here.
Noise.
Or 618. So in doing so, Ptolemy can figure out a whole bunch of chords. And just to not get too crazy with this, I just want to show you a surprising other one. If you know any chord, you can use it to find other ones. For instance, if I want to know what chord of 144 is, and I already know what chord of 36 is. So here's the 36-degree angle, but this one I arranged it as a, I arranged the central angle so that one side was horizontal. And this line segment is 0.618 approximately. Check this out. If I extend if I extend this line segment to make a diameter, this will be 144 degrees. And then if I draw this line, I'll get a big triangle, and this will be chord 144. How can we possibly answer that question? look carefully, and this is going to go back. People talk, oh, we memorized this and that, but what's the very first geometry theorem? Or we did some of the angles is 180 degrees, exterior angle theorem, isosceles triangle. But what was number 4? It was kind of like the first, like,
Triangle sum theorem.
that was the first one. Triangle sum, exterior angle, isosceles triangle led us to Thales theorem, which meant there was a right angle up here.
Yeah.
And that came up a lot of different times. Think about that. That came up throughout the course, Thales theorem. So check it out. This is a big right triangle that has a hypotenuse of 2. One leg is 0.618. So I can do x squared equals 2 squared minus 0.618 squared. So if you know any chord of any angle, you could find the chord of 180 minus it using this trick. It's really clever.
Can you leave that there for 1 second?
Yeah. I created a right triangle that had a hypotenuse of 2, because the triangle has diameter 2. And one of one of the legs of that triangle was chord 36, which I figured out from before. So if I already know chord 36 leads me to chord 144. By putting them, see, here's the 144 degree angle, central angle. So this line here is chord 144. I'll make it a different color.
Yes. It's 1.9.
Oh, you got 1.9 for it?
Yes.
So it's kind of funny. We have an unknown thing, a known thing, and a known thing. And we'd be in a lot of trouble until we realize, let's say I erase this line here. What I'm looking at is, only because of Thales theorem, it was theorem number 4, but 1, 2, and 3 were, real basic ones. And then Pythagorean theorem. Pythagorean theorem. It already, it comes up over and over. The prerequisite for this course is basically Pythagorean theorem and similar triangles.
Would the chords remain true in a circle other than a unit circle?
Well, the chord would be twice as big if it was a bigger. So nowadays we talk about the trig ratios, so they talk about like the ratio of, so in answer to your question, if I make the circle bigger, the chords will be larger. So, but if you divided the chord by the radius, you would always get the same thing. So if the circle was twice as big, the chords would become twice as big.
Okay.
Now, this is all I'm going to say about the development of the chord table, because the development is not quite as important as how to apply it. Now here, I wrote to you last night, if you would print up, you don't need to print it up, but sometimes it's annoying on a computer to be like trying to look stuff up on a table that's on a computer. Here is a table with all the angles. I did it in four pieces. Angles 1 to 45, or 0 to 45, 46 to 90, 91 to 135, and 136 to 180. And I have so Ptolemy made this table, and it was not easy to make this table. As we saw, we got 5 values: chord 60, chord 90, chord 120, chord 36, and chord 144. That's not a lot. He needs, not only did he get 100, not only did he get his table having 180 values, but he actually did every minute, which is a 1/60th of a degree.
Wow.
So he had to make a table that had 180 times 60. So big table. But for our purposes, there's 90 things. Let me show you how you use this table. And if you go into your Desmos, here's the code. Let me give it to everybody. hold on, there's the chat. I see someone in the chat. Yeah, the exam's at 9:15. I'm sorry, at 9:30. I know I said Tina says rather the easy questions. It is like a toss-up. I personally think I'd rather the easy questions, if I were taking the test. Also, I'm not saying that I make the test like exceptionally hard, like because there's a formula sheet. It's just if I was going to make a really easy question, like, do you know the formula for this? I would change that to a little more involved question that that applies the formula. It's just some of your teachers, so it's just you want to check, not does the student know how to stick numbers into a formula, but do they understand? Oh, I like to continue without signing in.
While you're plugging that in, did they stop at 180 because 181 equals 179? Like
Right. You don't need anything more than 180. That's right. The fact is that there's another reason why we don't need anything more than 180. That's going to come clear when you look at what type of question they ask.
Okay.
So here is an old school trigonometry question. X, unknown side, hypotenuse is known, 55-degree angle. Now, the table of chords, those triangles are not right triangles. What do you think you do? What value from the table of chords do you think is relevant to this question here?
Double 55.
Yes, 110, yes.
Yes. If you make a 110-degree angle, you can split that up into two right triangles that have 55 degrees in them. So I'm going to write down look up chord, we say CRD 110. So we go to our table and we see chord 110, according to the table, is 1.6383. And from this, we make a small right triangle that has a 55-degree angle in it. A 1 is the hypotenuse, and the other leg is half of 1.6383. So I'll just do 1.6383 divided by 2, and I get 0.8192. I'll just round.
I thought you said you couldn't double in half, though. It didn't work out properly. Why can you do it here?
That's not chord 55.
Oh.
That's not chord 55. Chord 55 would be if I extended this and went like that. That's not chord 55. It's
Right.
half of chord 110.
Okay.
Great question. Now you can do similar triangles because the 25 corresponds with the 1
Mhm.
and the x corresponds with the 0.192. So you say x over 25, x is the leg, equals 0.8192 over 1, or x equals 0.8192 times 25. And I end up with 20.5 as the answer.
So the point, half of the 0.8192 is base.
Yeah, the 0.1892, maybe I'll make this picture a little bit bigger. The 0.8192 was saying that if I had a 55-degree angle, and this wasn't a chord, this was just like a nice sort of right triangle, and I put a second one here, this big side would be chord 110, because that's the definition of chord 110, which makes this side here, the part of that small right triangle, half of chord 110, which is not the same thing as chord 55. So chord 110 divided by 2, which is 0.8192. So the chord table is not about right triangles. The chord table is about isosceles triangles. But every isosceles triangle can be split into 2 right triangles. You can see them because the x-axis is splitting this triangle. And this triangle here is a 55, 90, 35 triangle. So similar triangles. Now your calculator doesn't have a chord button on it. But what could you type into your calculator that would cause the number 0.8192 to pop out? There's something to think about. Again, the final is about doing this question, but now I'm asking like a deeper thinking question that would never be on the final, but sometimes it's hard for you guys to distinguish what's a thing that we're just talking about because it's like deeper, and what's a thing that might be on the final. Does anyone know what you could type into the calculator that would tell you 0.8192? There's no chord button, so you can't say chord 110 divided by 2.
It'd be arc sine. Or sine
No,
55.
but yes, it would be sine 55
Yes.
because sine 55, if the hypotenuse is 1, and I call this x, sine 55 is equal to opposite over hypotenuse. Sine is the ratio between, so some people say, well, let's go the other way. Chord 110 is 2 times sine 55. And that's true, but that complicates things a little much. For the homework and for the final, there's no thought about sine and how it's, I just wanted to mention that. Now I have a kind of tricky question. I want you to take a few minutes to, how are we doing time-wise? Yeah, I'm going to put you into groups for like a few minutes to think, this is a little different. There's something annoying about this one. What would it take? What would it take if all you had was the table of chords and you had a calculator that could multiply and divide and add and subtract and square roots and things like that? What would you, how could you answer this question with only a table of chords and the basic mathematical operations? Okay, I'm going to put you into, I'm going to let you choose your rooms, 6 rooms. 1 and 2, 1 through 4 for teachers, 5 and 6 for majors. So go into rooms for a few minutes and discuss this one. Okay, Marcus, is there a room you want to be assigned to?
No, I'm gonna jump into now.
Okay. Okay, everybody, welcome back. So I have here on the screen one idea. Chord 80 seems really relevant. And dividing it by 2 gets me the side there, 0.6428. The problem is this triangle is dealing with the opposite and the adjacent. It's the kind of thing like you want to use tangent for if we had it, but we don't. So one way of doing it is use Pythagorean theorem to find the third side of that little triangle, and then use similar triangles. So I write 28.5, yes. Now there is, maybe did any group realize that there is a sneaky way of getting this value that does not involve Pythagorean theorem?
I mean, can we use similar triangles or no?
Well, no, it wouldn't involve similar triangles either, actually.
And you use like chord of 50
That's
times
right.
2. Yeah, there you go.
Because this triangle also has a 50-degree angle in it. If I were to take the triangle and write it this way, 51, then this thing would be chord 100 divided by 2. So had you with your chord table, and you don't want to do the Pythagorean theorem, you actually come here and look up chord 100, which is 1.5321. Divided by 2 also gets you that. So it could be done without the Pythagorean theorem, believe it or not. But like on a test, I'd give you a calculator and say, do it however you want. I wouldn't, you'd be allowed to use that shortcut. But if that shortcut's like, a little too much of, sometimes we don't want like multiple ways of answering the same question. So you can use Pythagorean theorem, but just wanted to show you that you actually wouldn't need to, because the table of chords actually has information for finding this other side also. And since he went through the trouble of making the entire table of chords, it's nice to be able to use it, because then you don't, maybe getting the square root back in the day is really hard because you don't have a calculator. Now, we have seen now 3 questions that could potentially be on the final. Question 3 is this one. Question 2 is this one. And question 1 would be something like this. If chord 50 equals, hold on. If chord 50 equals 0.8452, what is chord 130? And for that one, it requires, maybe I give this picture even. It requires drawing that picture. X here, 2 there, right triangle, 0.8452. Pythagorean theorem, x is equal to the square root of 2 squared minus 0.8452. Now you might look at it and say, oh God, I got to memorize that. I don't think of it as memorizing it. I think of it as, if you know that chord 130 basically means that, and that chord 150 basically means that, chord 50, sorry, and that there's a sneaky way to put both of those together onto one picture, chord 130, chord 150, and then the right angle here makes a right triangle. 2 out of 3 sides are known, 1 unknown. I don't know. I suppose if someone tries to memorize chord 180 minus x is equal to the square root of 2 squared minus chord x squared, that would be like an annoying formula to try to memorize. I wouldn't think of it that way. So if you're thinking of this course as a bunch of formulas that you're memorizing one after the other, and you're saying, how am I going to memorize chord 180 minus x is the square root of 2 squared minus chord x squared? You're not trying to see the big picture of this is a relationship between 2 line segments that I managed to get together into the same triangle. I somehow got the unknown thing, chord 130, the known thing, chord 50, and another known thing, diameter 2, into the same right triangle, and then I could use Pythagorean theorem.
Sorry, Professor, could I ask you to go back to the other one really quick, where you had square root of 1 squared minus 0.6428? I feel like I'm doing something wrong. I keep getting 0.5976.
Oh, let me see.
Really wrong.
Did anyone else get that? Maybe I made a mistake. So 1 minus 0.6428 squared.
Oh, squared. Got it. I didn't see the
Okay.
square there.
Yeah, then take the square root.
Got it. Thank you.
Okay, so that takes care of, that's all I'm going to say about trigonometry, invented essentially by Ptolemy for the purpose of doing very complicated trigonometry with like spheres and things like that. But he needed a table of chords, and up until then they had like sort of table of chords, but not like Ptolemy did. So that's why that book is called the Almagest, which I think it means like, actually I forget what it's called, what it means. Now, here we are at 100 AD. We're going to be skipping ahead though to 1200. I'm sorry, 100 AD to 1200 AD. We're skipping ahead 1,100 years. So what happened between those times? A lot did happen. You had around the year 800, you had someone named Al-Khwarizmi, who the algorithm is named after. He wrote a book about algebra, what we call algebra now, and he used the word al-jabr. Officially, that word that algebra came from is the process. You know when you add stuff to both sides to solve an algebra question? That is called algebra, because that means like restoring, which is actually there's a different word when you subtract stuff from both sides.
How funny.
So he has a book that's like the art of algebra and this other thing, I forget what that one's called, where this one is officially algebra. Only the ones where you're adding stuff to both sides. The one where you subtract has a different name altogether. But that word algebra became our word algebra. So when you're doing algebra, you're actually doing a lot more than just adding stuff to both sides of an equation. A lot of stuff happened in between 100. A lot of it was happening in India and in various Arab countries.
Well, the Peacock book seems to think that India really kickstarted trig, right? They came up
Well,
with
in those countries, they really came up with even better formulas for calculating out the chords, which they refined into sine, cosine, and tangent. And in the Arab countries, they started developing, basically, Indian Arab countries started developing calculus. And in the Arab countries, well, we end up with the base 10 system, which are currently called the Hindu Arabic numerals.
So this is when the concept of zero was founded.
Yes.
Yeah, I love that video. I've played that video for my students. They're like, what? there was a time when people didn't know what zero was about? Like, yep.
Well, zero within China with the abacus, when they would write out what the state was, they sometimes put just like a little marking to represent zero. But the digit zero came up. The base 10 system is called the Hindu Arabic numerals. And once those were made, it made calculation so much easier. Some people say if only Archimedes had come up with the base 10 system, because Archimedes had to do all kinds of crazy calculations with the Greek numbers, and they were really hard with square roots and things like that. He could have done so much more even, but he didn't come up with it. Hindu Arabic numerals. So around the year 1200, someone named Fibonacci went and studied in those countries and brought back the Hindu Arabic numerals to Italy. So between 100 AD and 1200 AD, Europe was not pulling its weight as far as advancing math in any way that I know of. It was all happening in India and the various Arab countries. Fibonacci went and studied. He came back and wrote a book then called Liber Abaci, which means the book of calculations. And in it, he said, I went to the Arab countries, the Arab world, and I learned, the base 10 system. And then he wrote an extensive book showing how to do multiplying and dividing and dealing with fractions and various word problems involving, there was so many different currencies back then with all the countries and even regions. So like a lot of proportion questions, a lot of questions about like some guy has a will and he wants to give this son 2/7 and this son 3/7 and this son, 2/7, and how much should it be split by? A lot of word problems in the Liber Abaci. It's a pretty extensive book. It's considered to be one of the great works of math, the summary of the Hindu Arabic numerals and the collection of like 300 word problems that you can do with these calculations. That's quite a book. It's not, I tried to read it. Sometimes I say, it would be so cool to read this book. How hard could it be? Really, they don't know that much. They know about proportions, but it's not written like so well, like it's really wordy. And sometimes they just explain an algorithm, but they just say like, take this number, do this, 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 take this number, do this. And they don't explain like here's why, here's what you're doing. Because they don't really have yet algebraic, like an X. Everything's done in words.
Wow.
So it's not for another like 300 years until we get symbols for algebra, symbolic algebra. Otherwise, it's all words. Something unknown is added to this, So now we're into Fibonacci. Now, Fibonacci is most famous for the so-called Fibonacci sequence. And someone could put into the chat, if they know it already, what's the next number of the Fibonacci sequence?
$21.
It is 21. Each number is the sum of the previous two numbers. Now, this was studied. Fibonacci made this question, the question was not a number sequence, though. It was actually a question, a biology question. I actually have this in the, it's not a question for you to do, but if you go to the next page of the, of this, here's the question. Here's how he wrote it. A newly born pair of rabbits becomes capable of reproduction at age 1 month. After a gestation period of an additional month, the first offspring are born. The additional pair reproduces in the same fashion as the first pair how many rabbits will there be in the nth month? So we start off with one pair of baby rabbits. The next month, they become one pair of adult rabbits. The next month, there is one pair of babies, the new babies, and the old adults are still adults, which is two pairs altogether. The next month, these adults have another pair of babies. These babies become adults, but they don't have babies yet. So you have one babies and two adults, which becomes three pairs of rabbits. The next month, the two adult pairs make two baby pairs. The two adult pairs are still alive. This baby pair becomes adult pairs. So it's three adult pairs, becomes five. The next month, I'll say this way, the baby pairs become adults, so we have five adults. These three adult rabbits have three pairs of babies. So there's an assumption that no rabbits ever die, that every pair of rabbits is boy and a girl, and that they can reproduce, they reproduce in pairs like that. So that was Fibonacci's actual question about the rabbits. He did not come up with a general formula for calculating out the nth term. He did not study the interesting properties of the Fibonacci sequence. For instance, if you divide any two consecutive numbers, you get very close to the golden ratio. And the further out you go, the closer that gets to the golden ratio. Those are not things that Fibonacci studied at all. Those were not studied until the 1800s. Someone named Lucas, a mathematician, studied the Fibonacci sequence, named it the Fibonacci sequence, studied the properties of it, found the connection of the Fibonacci sequence to the golden ratio, and studied other Fibonacci-like sequences. Like if I start, instead of 1 and 1, I start with like 1 and 3. And what does that do? That's called the Lucas sequence. So that's all I want to say about Fibonacci. That's the true context of the Fibonacci sequence. Most people do know the Fibonacci sequence. It's a real famous sequence of numbers. Most people do not know that it came from a word problem involving very immortal and incestuous rabbits.
Oh, I guess I didn't connect that. You were actually coming up with the sequence by the rabbit. Ah, got it.
Yes. 1, 2, 3.
Yeah.
Anytime it's the adult rabbits is the sum of the adults and the babies from before.
Gotcha.
And then which is the total number. And the babies is the number of adult rabbits from before. So we add those two together. Okay, that takes care of Fibonacci. So today's lesson.
Professor, is there a way to make your screen larger? Because I have it on max size on my laptop and it's really small. I know I'm getting older, but it's hard to see.
So let me ask you, if I go like that, if I shrink it horizontally, does that cause the screen to get bigger on your end?
No.
Hmm.
It's cutting off the edges.
And what if I go like that? Now so you're saying it's different from other days even?
I feel like it's smaller. The text.
Well, this text is pretty small because I copied it from this is on your, so in your Desmos, you can, on your own end, take the, you could, oh, you know what? Look at that. Zoom. How about that? Thank you. How does that look
Yeah.
now? Okay.
Yeah, that's better because even the writing was,
I got
it's
you.
hard to, thank you.
See, and that's a perfect, I see that kind of question helped everybody because I didn't realize that I was zoomed out. Okay, now today's lesson is Ptolemy, Fibonacci, Napier, Napier, Fermat, and Euler. So we did Ptolemy and Fibonacci, and it's only 10:38. Now the next thing is Napier. So Napier is a mathematician in the oh, and just to mention, in between them, you might not have watched the video yet, but a very important thing happened in the year 1545. Cardano publishes a book called the Ars Magna. And in that book, he presents the holy grail of math at the time, which is an algorithm. Ars Magna. He figures out how to solve cubic equations. And so from BC times until 1545, all we have is quadratic formula for thousands of years. They had pretty much given up and said there probably is no cubic formula. But Cardano, and it's a very controversial story where some other guy figured out a formula for a similar cubic, but not the whole thing. And he told Cardano that formula and made him swear to secrecy, but he published it. He figured this one out. He couldn't resist. He published it anyway. He also figured out the general cubic formula, which math majors, your assignments involves that. And that's quite an undertaking. So in one book, Cardano does the holy grail of math, the cubic formula, and no one even was thinking about the 4th degree formula, but he does that also. And it turns out, you might say, well, when did the next person get the 5th degree formula? And the answer is never, because they proved in the 1700s or 1800s, I forget, they prove there can't be a ax to the 5th plus bx to the 4th plus cx to the 3rd plus dx squared plus ex plus f formula. So in one book, he publishes these two formulas. It causes a lot of controversy because he promised somebody he wouldn't reveal their formula, but he did it anyway, and there was a lot of controversy. You could watch the videos where I just talk about that, but I just want to mention it's an extremely important moment in math, cubic formula and 4th degree. Now you're going to watch a video. If you watch the 17-minute video, it does teach you how to solve these, at least if there's a 1 in front, which is all I care about. And you could watch the 17-minute video, or you could watch the 3-part hour-and-a-half video, or you could watch the 1-part 50-minute video. It's all how much time you have.
So to this day, they can't solve the 5th degree polynomials?
That's
Right.
right. It looked like an exact answer.
Right.
With certain ones you can, but not like generally. You can approximate the answer to whatever accuracy you want, but you can't get, if the answer is something with square roots and things, there's no formula for it, the way there is for like the quadratic formula. And this brings us to early 1600s. And a very important person named Napier. Napier was Scottish. And Napier created what's called now the log table. And the log table was your calculator from the 1600s. It eventually got turned into a mechanical device called the slide rule. Like right away in the 1600s, they had the log table followed by the slide rule. And the slide rule was what you carried around with you in college, if you were an engineer, from the 1600s all the way until the 1970s.
Wow.
They didn't have, and then in the 1970s, the affordable electronic calculator came out. But if you're in college in the 1960s, you have a slide rule. It looks like a ruler kind of thing. It has a nice leather carrying pouch that hangs on your belt. And for almost 400 years, Napier's invention was your calculator. So that was pretty significant. So what is this log table? The log, when people learn, when the log table was invented, it was based on such a simple idea that people were so amazed. They couldn't believe it hadn't been thought of earlier. So what is this simple idea? It goes like this. Imagine I made a chart with all the powers of 2. It would be easy to make because all I have to do is keep doubling my previous number. Whoops, why did that say 8? Okay, what could I do with this chart? Well, for one thing, I could multiply 2 numbers together. For instance, imagine I want to know what 4 times 8 is. And 4 and 8 both happen to be numbers on my in the column on the right hand side. So that means I could write 4. According to this table, 4 is 2 squared. And 8 is 2 to the 3rd power. And there's a rule, of course, we learn it maybe in 6th grade, that when you multiply 2 things, I'll write x to the a times x to the b is x to the a plus b. So 2 to the, if they have the same base, you add the exponents together, 2 to the 5th. And then we go to this number and locate it in the end table. And the answer is right here. If I don't know how to multiply, if for whatever reason 4 times 8 is a difficult multiplication for me, having this chart enables me to accomplish it with the simple 2 plus 3 is the only actual calculation I did. It does look like the Egyptian multiply with the chart and what corresponds to what. Okay, what else can we do with this chart? Well, I could do 128 divided by 32. 128 is 2 to the 7th power because it's on the chart. 32 is 2 to the 5th power.
We subtract the power. Yes.
That's right. The rule that they teach you in maybe 6th grade, and the rule's kind of obvious. Like, you know, if you 2 to the, if I had a bunch of 2s, 1, 2, 3, 4, 5, 6, 7, and I have 5 2s underneath it, and I cancel them out, all that's going to be left is 2 of them. But the official rule is you could subtract the 2 exponents. And now I don't know 2 squared, but I have a chart for it. So having this chart allows me to multiply 2 numbers together by, the only math I actually need to do is adding 2 exponents. And adding is easier than multiplying. And it enables me to divide any 2 numbers with 3. I mean, I have to use the table 3 times. But subtracting 7 minus 5 is easier than dividing. There's more things you can do with this table besides multiplying and dividing. If I want to do 8 to the second power, and let's say 4 to the third power.
We
There's a
write 4 to square.
x to the a to the b
Mhm.
is the same thing as x to the a
Times 3.
times b. So 4 to the third power, 4 is the same thing as 2 squared. 2 squared to the third is the same thing as 2 to the sixth power. Yes, I needed to multiply. That's true. And 2 to the sixth is 64. So you can raise things to powers by multiplying. The only calculation was needed was 2 times 3. Now don't say, oh, well, do I need a log table to do 2 times 3? No. But the point is, raising to powers requires 2 table lookups and a multiplication. Multiplying 2 numbers requires 2 table lookups in addition and a third table lookup to go backwards. Division requires 2 table lookups, a subtraction. So presumably those 4 things are easier than dividing. And finally, if I want to take the cube root of 64, I'll say square root of 64. 64 could be written as 2 to the 6th power.
Mhm.
And the square root,
1/2.
yeah, you end up basically cutting the exponent in half. And then find 3 on the table to get the answer. So square roots, which is, we learned that square roots is quite a complicated process. But to take the square root, you just take half of the exponent. And then the final thing I'll show you is cube root, which we've never even talked about, is 2 to the 6 to the 1/3, which is basically 2 to the 2nd, which I have on my chart. So square root was accomplished with a division, 6 divided by 2. And yes, I had to do the table lookups. And cube root was done, the only real calculation I did was 6 divided by 3. Now we could all admit that dividing by 3 is easier than taking the cube root of something. Maybe not, maybe you say, well, this is an easy one. But I'm going to show you the power of this in a minute. But for now, this is the power of having a table like this.
Right.
But the 2 to the n table is a bit limited. Because what if I want to do 5 times 3?
The problem
Or
is,
5 divided by 3? I
wouldn't they?
can't.
Yeah,
Because those numbers, I can only do stuff with numbers that are on this table. And if I want to do the 5th root of 64, and I do 2 to the 6 to the 1/5 is 2 to the 1 is 2 to the 1.2, I'm stuck also.
Mhm.
Because I don't have a 1.2 here. So the 2 to the n table is not good enough. But the logic that I'm teaching this topic by using first a simplified chart that's not as powerful as the one we're going to get. But what's funny about it is that it is based on 3 or maybe 4, if you want to call it that, facts that you learn, or 6th, 7th, 8th grade, I don't know exactly what year. X to the A to the B is X to the AB. And I'll write it like this way. The bth root of X to the A is X to the A over B. Those, okay, 8th grade. So those are 4 things that are from 8th grade math. I might give those, for instance, because I was gonna, like if I give these things on the final, like here's a reference, just 4 facts. Because I would never ask a question, what's 2 to the 3rd times 2 to the 5th is 2 to the blank. That's not, would never be a question. So I could give you this because that wouldn't remove any question I was possibly gonna give. So I'm gonna say maybe give you this on the final.
Did Napier actually develop these 4 rules? Is he the author of them?
No. Those 4 rules are well known for thousands of years.
Okay.
But what Napier, what his brilliance was saying 2 isn't a very good base because it skips so many numbers. Now you might say, well, if I don't want to skip numbers, I could get sneaky, like I could put like 1.5 here and take the square root of 8. Then I got to deal with square roots. That's its own problem. Plus, square root of 8 is not a nice number anyway. I want to have more numbers here. Now 2's no good. 3's even worse. 4's even worse. 1 is the worst of all because 1 just keeps on becoming 1. And if you want to say, well, I'll pick something between 1 and 2, like 1.1, it's really hard to raise 1.1 to the 1st power, to the 2nd power, to the 3rd power. So if we tried 1.1, for instance, let me go over here. Oh, wow. Doesn't let me type in there. How could that be? I'm in a window. So strange. I could type into other things. I could type into forms. Hold on a second.
Maybe refresh it.
Okay, let me try that. That is, whoops. Now I'm full screen. Hold on a second. Let me just. You know what I'm going to do? Oh, here we go. New tab. I don't know. Here. So here's a spreadsheet just to show you what happens if I try to do another base. So here's going to be my power. Here's going to be 1.1 will be this. No, it's going to be 1.1 to the powers. I'm writing 1.1 there. So I'll make this 1 and I'll make this A1. Not A1.
A2.
B1. And then for this one, I'm going to say equals A2 plus 1. And for this one, I'm going to say equals B2 times A1 with, sorry, equals B equals
B3.
B2 times B1. I want to go back to the top and I'm going to put these dollar signs. Now, if I copy this all the way down, okay.
Mhm.
So what you can see here is that, you know, I have 1.1 and 1.2, about 1.3. You know, it jumps a bit. So maybe I just want to get integers. So I have something around 1, and then eventually I get something around 2, and then eventually I get something around 3, and eventually I get something around 4, and eventually I get something around 5, and eventually I get something around 6, and eventually I get something around 7. And if I kind of just delete most of these, how many does it take before I get up to like, I get up to 100? Well, it's a problem because look at how many numbers I end up skipping eventually. 66 jumps straight to 72. So I need a base closer to 1. So I make it 1.01. Now it takes all the way until I get
Holy cow.
to 70. It takes all the way till I get to 70 to get to 2. And 3 doesn't pop up until 111. And 4 doesn't pop up until 140. And after 245 rows, I only got to 11. And just to see, I get up to 100 after 463 rows. So that actually is promising as a base. If, you know, multiplying by 1.01 is annoying, but if you did that 400, around 500 times, and then you would just throw out, or you would hide, let's say, all of these between 1 and 2, because you don't care about those maybe. Then you would hide all the things between 71 and 112. And then you would hide all the things between 112. I'll just go out to 4.
Mhm.
And you would have a chart that would have 1, 2, 3, 4. You know, it might be a little bit more useful to you. Now, this isn't, I'm still not up to what Napier actually does, because back in Napier's time, the calculations that they were most interested in was multiplying, dividing, square roots, cube roots of trig values. Like they wanted to know, like, what's sine of 40 times sine of 80, that kind of thing. Or what's the cube root of sine of 40? Well, sine values are always between 0 and 1. So he wants to be able to do stuff like 0.37 times 0.45, or 0.45 divided by 0.22, or what's the square root of 0.45, or what's the 8th root of let's say the 7th root of 0.45. These were the questions that were very important for mathematicians at the time. And if you have the ability to do those, and you need to do 37 times 45, well, you could just do 0.37 times 0.45 and multiply the answer by 10,000 or whatever. So if you have the ability to do decimals, numbers between 0 and 1, you could do anything. The questions we're going to do, I'm going to teach you how to do, are always questions like this. We're going to only do operations with numbers between 0 and 1. So look at what Napier did. And this was a really, really smart idea. Let me unhide all these. He made his base. See, if you make your base a decimal, and here's 0.9, I want to have like 0.9. I really want to have, ideally, I want to have 100 values, 0.99, 0.98, 0.97, all the way down to 0.01. That's my goal. So this doesn't have 0.99 on it. So maybe I'll make my base 0.99. See, 0.99 is here. 0.98 is next. 0.97 is next. 0.96 is next. 0.95 is next. 0.94 is next. 0.93 is next. 0.92, 0.91, 0.90, 0.89, 0.88, 0.87, 0.86. But now something interesting happens. After the 14th one, 0.85 approximately is not for 2 more. So he deletes, this column. Now look what happens. When do we get down? Well, we get down to 0.01 after 400, approximately 445 rows. But maybe he wants 0.98. He doesn't want 0.97029. He really wants 0.97. So instead of using 0.99, he uses 0.9999. So that gets us, we have to look a long way between 0.9 even appears. It takes all this. 0.9 finally gets there on the 100th row. Put a star here. And 0.98 doesn't happen until the 202nd row. And he's gonna need a lot of rows because after 465 rows, he's only at 0.95. No, he's gonna need to take many years because he doesn't even use 0.9999. He uses 0.999999. He's gonna need
How many nines?
6.
Okay.
Here after 1,000 with the 4 nines, it only makes it to 0.90. It's going to take 50,000 calculations to get his chart. But lucky for you, I have provided you with that chart. So bring up Napier logs. So my table is for 0.9999, and you can see after you raise it to the 100th power, you get just regular 0.9 because it gets smaller each time. When you multiply by something less than 1, it gets a little smaller. After 202, it gets to 0.98. I showed you those two actually. So we basically throw all this work is done, but the majority of it is thrown out. And he eventually, after 46,000 calculations, he gets 0.01. So this would have taken 46,000 calculations, and we threw out it took 46,049 calculations, but we only kept 100 of them. The other 45,951 calculations were thrown out. And we're left with this. Okay, let's take a 10-minute break. When we come back, we'll look at how we can use this chart to do some calculations. Okay, so I'll see you in 10 minutes. Okay, everybody, welcome back. Now, this was a lot of theory. I wanted to give you, the motivation behind this chart and what these numbers mean. Like, if I asked you, how could you verify that 513 is the right number here? You should understand that, okay, that means that 0.9999 to the 513th power equals 0.95, something like that. But when it all comes down to it, there's only 4 questions that I might ask about this topic. Oh, wait. Sorry, I lost my feed. Let me try this again. Okay, let me go back. 612749369. On the homework, on the final, there are only 4 questions I will ask. And they are: use the log table to multiply these 2 decimals together. Use the log table to divide these 2 decimals. Use the log table to take the square root of this decimal. Use the log table to take the cube root of this decimal. So let's start with this question.
Can you say again? Sorry.
Well, you'll see them here. Multiply, divide, square root, cube root. So let's look. Multiplying, use a Napier log table to calculate 0.27 times 0.31. So the idea is 0.27, 0.27 times 0.31. 0.27 is 0.9999 to some power. And 0.31 is also 0.9999 to some power. And the answer is 0.9999 to some power. So what goes in those boxes? Well, that's where the chart comes in. So for 0.27, we come over here and we find that 0.27 is over here, 13093. So we come here and write 13093. So that was looking up 0.7 in the table. And 0.31, we come over here, it's right near it, it's 11711. So all we did was we looked up, we located these 2 numbers in the table and found what the corresponding exponent was. And now we add the exponents together. That's the only actual calculation we need. Two, 4, 8, 0, 4. And finally, we come over here and we see is 24804 anywhere? Well, it's not going to be exactly there because the real log table is like books and books, of 0.999999, and they get every like thousandth, so it's hundreds of pages long. But for our purposes, we look for the number that's closest to 24. Yes.
78, yes.
It looks like
5, yes.
It looks like 0.08 is as close as I could get. That's as 25256 is as close as I'm getting.
Mhm.
So the answer is 0.08. Of course, if you take an actual calculator and multiply 0.27 times 0.31, you do get 0.0837. So what is this? It required looking up 0.27 on the table, 0.31 on the table, adding, and then trying to find 24,804 on the table. Unfortunately, 24,804 wasn't on the table. If I did 6 nines, it would require, 100, it would require 1,000,000 calculations to get the table, just to get the 100 entries of the table. But it would be, well, we would want 1,000 entries then, 0.01, 0.001, 0.002, 0.003, up to 0.999. We need 1,000 entries. And we actually could have done 1,000 entries for this one also and gotten more accurate. But I just wanted to give you the 100 number log chart.
So Professor, when you get the 0.24804, you just pick the number that it's closest to, right? I mean,
Yeah, because we don't know what 0.9999 to the 24804 is.
okay.
Question, Professor.
Yeah.
Our value is the midpoint between two values on the table.
Oh wait, it's really it's not clear. Say that again.
Yeah. If our value is midpoint between two values on the table, so we need to do the average.
Do you wait? It's between two numbers. You're saying 24804 is between two things?
Yes, it's on the same distance between them. For
You could
example.
pick. If you picked either of them, it would be okay. So if you had because it's not exactly in there. If you said it's in between 0.09 and 0.08, that would be okay also.
I said between 24078 and 256, we have a number. It's exactly on the same distance between them. We need to do the average 0.09 plus 0.08 over 2.
Average? No, we can't really. It doesn't quite work that way. So if you want to write though, it's between. If you wrote 0.8 or you wrote 0.09 or you said it's between 0.08 and 0.09. Either of those is fine, because the number is not on the chart, and it's hard to. It's not perfectly like linear, like it's not halfway, and even a proportion doesn't quite do it. So I'm going to want you to try to find the one that it's closest to. But if you were off by 0.01, I would accept that. And if you wrote that it was between these two, I would accept that also. Those are the three things that would be.
For example, if we have 24667.
Yeah, it's halfway between. It doesn't mean, it does not mean that the answer is halfway between, because it's like not so-called linear. So we wouldn't be able to make that conclusion that it's exactly. So it's really hard they call that interpolation. So, but that is actually a hard question. How do you, if you don't have an exact thing, can you use two consecutive things? Let's move on to the second question. This one is asking, what's 0.83 divided by 0.29? Let's put you into the groups to get your approximate answer for that. So let me breakout rooms. Sorry, everyone. I had to bring you back because I realized something. I don't want to do any questions where the answer is not a decimal. So if we change this, if we change these around, that's a better question. And so I'm gonna make 0.29 divided by point. I want all my answers to have decimal answers. There is a way to do it if they don't, but it's kind of complicated. So let's switch those two things around, and I'll do on the homework also. I'll switch them around.
Why were you doing?
So we're doing. Oh, sorry. So we're doing 0.29 divided by 0.83 instead. Sorry, I realized that when I started to do it. So back to the rooms to do the modified problem. Thanks. Okay, welcome back. I hope that you got something like this. We looked up 0.29 on the table, found that it's 12,378. Looked up 0.83 on the table, found that it's 1,863. Subtracted those, old school, got 10,515. 10,515 wasn't on the chart, but 10,498 was on the chart. And that corresponded to 0.35. And that's the answer. And that is actually extremely close. The actual answer is 0.349.
And it was okay to say between 0.35 and 0.34, correct?
That's right. Now, multiplying and dividing, you know, that's good. But this is considered one of the greatest inventions in the history of math because it can also be used for square roots and cube roots and fourth roots and whatever roots you want to take. So let me take you through that. So the square root of 0.83 is the same thing as 0.9999 to the, now we had 0.83 from before. It was 1863.
Yeah.
So 1863 square root of that.
Yeah.
Which is when you take the square root of something that's like an exponential form, you end up dividing the 1863 by 2, which, you know, no way around it. We're just gonna
931.5.
931.5.
Yes.
Now 931.5 is not, of course, going to be on the chart. It's a decimal.
Yeah.
However, we look.
It's close to 0.91.
Let me see. Wait, hold on. I got.
Mm-hmm.
Oh yeah, it's pretty close. So it's
Yes.
around 0.91. So
Yes.
9.3. It's in between 0.92 and 9.1. So we say,
Okay.
if you like to say between 0.9. Wait, sorry, I got myself confused.
Yeah, go back.
9.2 was 834 and 9.1. So between 9.1 and 9.2. If you go to an actual calculator and
It's
type in,
0.91.
if you type in square root, if you type in square root of 0.83, you do get 0.911.
Yeah.
Between 0.91 and 0.92.
Beautiful, nice.
And finally, if you want to do another root, like the cube root of 0.83, it's the same thing. 0.9999 to the 1863. I think it's 1863.
Yep.
But the only difference is we
Divide
divide by 3 and get 621. Which when we go to our chart, we find it's very close to 0.94.
Yeah.
And if you want to check and you go to your calculator and do the cube root, does my calculator have that? Yeah, my calculator has cube root. Oh, and cube root. It's weird. Second cube root. Cube root of 0.83. Oops. Well, my calculator is not so good for it. Let me bring up a Desmos.
Yeah, it's 0.939779637. So it is very close. Wow.
Yeah, so practically 0.94. So when Napier came up with this, a quote that someone made was that Napier, he made people be able to do their calculations so much quicker that he, quote, doubled the life of the astronomers. So no, they didn't live to 180 years old, but they lived happier lives because they didn't have to do square roots and cube roots so hard anymore. As I mentioned, huh? As I mentioned, this very quickly, within the next 50 years, they changed it to base 10. And then we get what's called our common logarithms that you learned in school. But Napier's logarithms were based on like a number slightly less than 1. But within 20 years, someone named Briggs came along and he changed it to base 10. Again, within 20, 30 years, they invented the slide rule, which was based on this idea. And the slide rule was in continuous use for the next 400 years as your calculator. So that's definitely worthy of a spot in this course. Okay.
And in a way, he made mathematicians more productive, right? They could do other things instead of just beating their heads up on these calculations.
Yes. Now it became a big task then to make more accurate tables. And there were people whose jobs it was just to, you know, now we want a table that's based on, you know, that has every 1,000th points 0.00001, you know, and we need a bigger table. So making tables was like a full-time job. I believe there were people that was their full-time jobs, making these tables, because the tables were like books. They weren't just a single page. Okay, now we fast forward.
I have a question. So do we bring these sheets on Tuesday?
I'd provide it.
Okay.
Yeah, so you would get these tables on the final. And these 4 questions, you know, what we've seen today are so far 7 potential final exam questions. Someone who was away from their screen for a second asked about how does knowing chord 50 equals whatever 0.7 help me find chord 130? And the answer was, you can put chord 50 and 130 together in the same
Right triangle.
circle, and that would become an actual right triangle with a hypotenuse of 2, a leg of chord 50, and then you could use Pythagorean theorem to figure out the missing leg, which would also be chord 130. I don't know if that's what chord I don't know if that's what chord 50 is. Chord 50 is 0.8452. Okay. We now jump to the mid 1600s. I want to say a little bit about a very famous name in the history of math, which is Fermat. Fermat he's known as the great amateur because he was not a mathematician. He was a lawyer who did math as a hobby. But he was a great mathematician. He and Descartes had a huge rivalry. He always got the best of Descartes. Descartes was an important mathematician, came up with the Cartesian coordinate system, but Fermat, it's like that movie Amadeus where you got like the Salieri and the Mozart, and one guy it just comes easily to, and the other guy has to work so hard for it. Fermat was just so good at it. So Fermat did so much in math, but the thing that he's most known for is this. He was reading an old Greek math book, and he was studying about Pythagorean triples. And what would happen if you took a squared plus b squared plus c squared, which has so many solutions, and you just made a slight modification? You just changed all the 2's into 3's. You know, there's so many perfect cubes. 1/3 equals 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed equals 64, forever. Surely there are 2 numbers on this list that equal a 3rd number on that list. if I get to use humongous numbers with hundreds of digits. But Fermat wrote down in this margin of this book, it is impossible for any number which is a power greater than the second to be written as the sum of two like powers, saying, no, you're not going to get a to the third plus b to the third equals c to the third. You can't use 0. You're not going to get a to the fourth plus b to the fourth equals c to the fourth, no matter how big your numbers could be, or any power. 2 is the biggest. Well, a to the 1 plus b to the 1 equals c to the 1 has infinite solutions. And then statement of theorem, statement of conjecture. So now we want the proof. I have a truly marvelous demonstration of this proposition, a proof which this margin is too narrow to contain. Because he's, there's like a book that he's reading and it has text in it, and he just was making notes in the margins. They found this note in 1655 after Fermat was already dead. He was already dead. So this became known as Fermat's last theorem. Because all of his other things that he wrote like this, over the years, they were able to either prove or to prove that he was wrong. Because Fermat was wrong about other things. Most famously, he said 2 to the n plus 1 is always prime. Fermat said that. And when you put n equals 1, you get 5. And you put n equals 2, you get 17. And you put n equals 3, you get 2 to the 8th plus 1. Hold on. You get 257, which is prime. And you put n equals 4, and you get 2 to the 16th plus 1 is 65537. So it was true for the first 4 values of n. And he said it's always true. So when you put 5 in, 2 to the 32 plus 1, you get this very large number, 4, 2, 9, 496, 7297. Which, as far as anyone knew, it's 4,294,697,297. So everyone just assumed that Fermat was right. At that time, it's really hard to check if that number is prime it would take a really long time to find the factors of 4 billion. Now we will fast forward to the 1700s and our final mathematician, whose name is Leonard Euler. It looks like people say Euler a lot when they see it spelled E-U-L-E-R, but you pronounce it O-I-L-E-R. So he lived from 1707 to 1783. And Euler showed that Fermat was wrong because he said that he noticed that this number is divisible by 641. So it's 641 times 6700417, 00417. So that was an example of something Fermat was wrong about. So maybe Fermat was wrong about this one also. Well, for the next 350 years, proving or disproving Fermat's last theorem was the holy grail of math. So for 350 years, people tried. Euler proved that it was true for n equals 3 and n equals 4, but that's as far as he got. Other people figured out some other limited cases but a general proof eluded everybody until 1994. In 1994, a Princeton University professor named Andrew Wiles proved Fermat's last theorem and proved it was true, because someone also could have proved it was false and maybe found a set of numbers that makes it true. Could have found some giant number to some giant power plus. Andrew Wiles proves it in 1994. His proof was several hundred pages long and required math that was invented in the 1950s, 60s, 70s, and 80s. So if Fermat had an actual proof, it wouldn't have been that proof. Some people are still trying to figure out what Fermat's proof, if he had one, would have been based on the kind of math that they had back in the 1600s. But Fermat's last theorem is proved. You need a PhD in a very specialized branch of math to understand the proof. So it's not very satisfying, because Euler's proofs of n equals 4, n equals 3 are much easier to understand. Wiles' proof is not comprehensible to the person in math who doesn't have a PhD. So any history of math course needs to mention Fermat's last theorem, the holy grail of math for 350 years. And this brings us to the final topic. An example of something that Euler did. So Euler was the most prolific mathematician in history. In his 80 years of life, he produced more math, if you write, like books, volumes, than all of math from the beginning of time until him. So he personally made 80 like encyclopedia-sized books full of math. And that's, if you added up all the math from beginning of history till him, it was that much. So he doubled the amount of math. No topic was below him. Like he found interesting things in every single topic, no matter how like trivial it might seem. Someone would ask him a simple seeming question, and he would develop an entire theory and use it to invent a new branch of math that would answer that question and answer much harder questions. So Euler is my favorite mathematician because he is so, every type of math interests him. Everything, he finds something interesting in, no matter how like unimportant some math thing might seem to be. He would get into it. Euler went blind when he was about 60 years old, and he continued doing the math while blind, dictating it to his assistant. So Euler is a great name to know. You definitely want to pronounce it properly. Euler, not Euler. The only problem I'm going to show you from Euler, and that will end this course, is what's called the 7 bridges of Königsberg problem. Come on, wait, let's see. Copy. So Euler was visiting a city in Russia that was called Königsberg at the time. It's not called that anymore. And they had, just to make this more clear, they had a river that went through the town. This thing is the river. And in the river created an island in the middle. So here's an island in the middle. And there's land out here and out here. And out here. And they built some bridges. And they happened to build 7 bridges. And the thing that people would try to do for fun is, let's say I'm standing here, to try to walk around to cross every bridge and only do each bridge once. So, we try. Okay, cross one bridge, cross the second bridge, cross the third bridge, cross the fifth bridge, cross the sixth bridge, and now I'm in trouble. Because if I go this way, I'm stuck in landmass D. I can't get to the seventh bridge. On the other hand, if I go this way, I'm stuck in landmass B, and I can't get across this bridge. Maybe if I start, maybe if you helicopter me to the island, I can do it. But I run into trouble again, because if I go this way, I'm stuck. And if I go that way, I'm also stuck. How are we doing on time? So for time purposes, I'm going to tell you that you could try all you want on this problem. And you'll never answer it because it is impossible. But some situations might be possible. If I throw another bridge on, for instance, I throw another bridge on, maybe it's possible now. Let's see. Hold on. Yeah, check it out. Oops.
Don't get lost.
Hold on a second. No, this one should be possible, so let me try again. Let me not, there we go. So sometimes it is possible. So what distinguishes when it's possible versus impossible? Here's one with 15 bridges. If I told you, yes, this one is possible, but it's really hard, you would struggle a lot to answer it. Because if you could try, and it might be possible, but only if you're careful about it, So I'm going to tell you what he came up with, the criteria for when it's possible, when it's impossible, and if it's possible, what the strategy is for doing it. And it's very much related to a game you might have played when you were a kid. It's a game where they say, try to draw this, where once you put your pencil down, you can't pick it up again. You can't trace over the same line twice. But if you try to start up here, you get stuck. If you try to start up here, you get stuck. We didn't have the thing on the bottom. So this is an example one that's possible, but only in certain ways. If you try to do this guy with it's a house with nothing on top, it's impossible. You will get stuck no matter where you start, no matter what you do. Euler figured out this problem, and you might say, well, who cares? It's a question about maps. It's a riddle. But in doing so, he invented an entire branch of math that is now called graph theory. here comes the insight now. I'm gonna teach you. I'm just gonna jump straight to the, this usually makes for a nice activity, you know, have you hammer away at it. But since there's only 14 minutes left. Okay. So a significant thing about this riddle is how many bridges are there leading to or coming out of each of these so-called land masses? There are 3 coming out of D. There are 3 coming out of landmass B. There's one here, one here, one here. There are 3 bridges coming out of landmass C. And there are 1, 2, 3, 4, 5 coming out of landmass A. Now, if I start somewhere randomly, I start in D. D has an odd number of bridges, which means if I start in D and I leave it, I come back to it, and I leave it, I must end somewhere else. Okay, if I start in D, I must end somewhere else if it has an odd number of bridges. So that's it. That's, you know, and that's true for any of these. They all have odd numbers. So if I start in C, there's no way I could end in C because I leave C, enter C. On the 3rd bridge, the odd number bridge, I have to end elsewhere. So you say big deal. So I don't end where I start. It doesn't say you have to end where you start. That would be an even more challenging problem. I don't care if I end where I start. But here's the thing. Let's go back to D. If I start anywhere but D, elsewhere, I have to get to D, leave D, and come back to D. So if I start outside of an odd number thing, I must end up inside of it.
So now you're trapped.
I'd be trapped here, but I don't have to necessarily do that.
Okay.
But the thing is, let's come over here. Here's the 15 bridges. Let's count the bridges in this situation. 3, that's an odd number. 4, 1, 2, 3, 4. 1, 2, 3, 4, 5. There's a bridge here, so 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, yes, 8. Now notice this has 2 odd numbers. That's very important. If there are 2 odd numbers, so if I start in D, I must end somewhere else. If I start outside of D, if I start anywhere outside of D, I must end in D. On the other hand, if I start anywhere outside of E, I must end in E. So if this is possible, I must start in D and end in E, or vice versa. You must start from one odd and end in the other. And as long as you're careful not to totally burn all your bridges,
Literally.
yeah, you will do it. So knowing that helps you answer this question. Let me show you that again. There's multiple ways to do it. But the trick is to start in one odd and end in the other odd. So the 2 odds were D and E. If I start in one of them, and I have to be careful. I mean, you might mess up if you're not careful enough. But as long as you know, if I start here and I just get careful not to like get trapped. If I'm just careful not to get trapped, starting in one odd and ending in the other odd will work. Now, when it comes to the 7 bridges, there's more than 2 odds. More than 2 odds. So it's impossible. In general, no odds, very easy. You start anywhere. 1 odd, it's impossible to create. No map can actually have this. Don't want to tell you why, I'm just telling you that now. 2 odds, start in one, end in the other. It may take a couple of chances, but you will get it. And finally, more than 2 odds, it can't be solved. Those are the only things that can happen.
What did you write next to 1 odd?
It's not possible to create a situation where there's only 1 odd. So it's kind of complicated. Why? So that's not even a case, because you will never see a map that has only 1 odd. It's hard to explain why. So I'll just tell you that just won't happen. Either you'll have no odds, in which case it will be totally easy, or you'll have 2 odds, in which case you'll know if you start in one and end in the other, you'll get it pretty quickly. And more than 2 odds, you won't even try, because it will be impossible. Remember when I threw on this 8th bridge? So now it became
Right.
4, 3, 5, 4.
Because it
So
really gave the bridge to both C and D by putting the 1.
Yeah. It fixes 2 of the things. So I'm going to be careful. You see, I don't want to go back here. I'll get stuck. So go like that.
And you call this game theory is what you called it?
Group theory.
Group theory.
I'm sorry. Graph theory.
Graph?
Not-
Like,
Yeah, not the kind of graph with like X, Y, but graph theory is where there's like dots and there's like lines connecting them. And we study like how those things can interact with each other. So that's called graph theory.
interesting.
And he basically invented it by doing this problem. Remember the childhood game? This versus this. If you treat these dots as the land masses,
Yeah.
and these lines as the bridges, this would be 2, 1, 2, 4, 1, 2, 3, 2, 4, 4, 3, 3. So the only way to do this one would be to start here and end here. Whereas this one has 3, 3, 3, 3, too many odds.
Right.
So that one, it doesn't matter if you try all day, you will never do it. And just to round it out, the house with 2, this one has no odds. And not only could you do it so easily, but you could actually end back at your starting point. So no odds is totally easy. You could start anywhere and end anywhere, even back at yourself. 2 odds, you can only do it if you start at 1 odd and end at the other. More than 2 odds, you'll never do it. Exactly 1 odd can't happen. It's kind of difficult to explain why that is. Here's 2 odds. And when I add like another edge, these both turn into 2s.
It's kind of like when you had the 2 3s on that 7 bridges, right? They turned both into 4s. Is it the same concept?
Yes. When you add, when you add a bridge, 2 things change. You know, if I'm adding a bridge, even if I add another city, if I add a bridge, this one is 0 right now, and I add a bridge, this turns into 3, this turns into 1. So there's 2 odds. But if I add another bridge, this turns to 4 and 2. So it's not possible to create a situation where there's and nowadays in the modern Königsberg, they've changed the bridges. Modern Königsberg, it is possible now.
Right. Well, one of them got destroyed in one of the world wars or something. That's why you can do it.
And now it's got exactly, so modern Königsberg, you can do it, but I believe you have to start on the island or end on the island. I read something about that. That now there's exactly 2. Now there's exactly 2 odd land masses. So but one of them is the island. So you either have to helicopter yourself to the island, or you have to start and be trapped on the island. So, okay, so that serves for a really fun thing. So you could imagine on the test, I'll give you a map and say, either explain why this is impossible, more than 2 odd, or show me a path. Start at one, end at the other.
Oh, so just the pathway will suffice. Okay.
Yeah. Okay, and with that, and with 3 minutes to go, we have, no, you should bring a calculator with you. So the final exam's at 9:30. It's in North NAC classroom. I'll tell you the room number. I mean, I think it's 415, but I forgot exactly. Get there. I'd recommend aiming for an hour early in case you get lost, you haven't been there. You really don't want to be late for the final. So what we've covered is math starting in 1600 BC with the Babylonians and the Egyptians. We went through the Egyptians, Chinese, spends a lot of time on Greeks, and today we fast forwarded all the way through to the 1700s with Ptolemy's table of chords, how he invented trigonometry. Yeah, Euler would have liked having a computer for sure. Although his nickname was the calculator. And when he died, someone said something like Euler, ceased breathing and calculating. Euler ceased breathing. Let's see. Let's quote on that. Euler and calculating or something like that. Where do they say it? Quotes about Euler. Read Euler. He is master of us all. Someone made a quote in his eulogy, Euler ceased breathing and calculating. Or something like that. So I have to leave now, but we'll be back on Monday, although I might be a little late on Monday, so don't get nervous. I have to return a rental car and I have to take a train back. And if I miss my train, I might not be here till 10, but I'll keep open I'll open the room for final exam review. So I hope you liked today. Today was 8 questions we learned. Doing an Euler Bridge of the Königsberg type problem, doing those 3 questions about the table of chords, and the 4 questions about the log table. If you can do those 8 questions, there's 7 of them on the homework. Those are the only things that would come up on the final. I wouldn't get into why did Napier choose 0.9999 instead of 1.001, nothing like that. Okay, I gotta run. I'm sorry, I came early today, so I'd be able to leave right now. I'll be seeing you on Monday.
Thanks.
Professor.